Okay, let's go ahead and get started. Thank you all for coming here nice and early on a Tuesday morning. Today's talk's a nice follow-on to yesterday, which was a brief introduction to causal inference. Today, we're going to try to consider how we extend that basic approach to a more longitudinal setting, probably to questions that you are maybe a little bit more interested in answering. And run through some examples in R, some fairly simple examples in R about how to do it. So just a quick show of hands, who uses R, is familiar with R? Awesome, excellent. So we can go through this a little bit more quickly. Who's used RStudio Cloud? You have? Cloud, okay. I'll show you, it's not a big deal, I'm just interested. Okay, so just a little bit of schedule. We'll go over defining the longitudinal causal question first, because honestly, this is the most difficult part of any research endeavor in causal inference. And then following on, implementing the chosen statistical approach to try to address these questions. We'll start with a very basic case study on smoking cessation, take a break, and then follow on with 2 more case studies. So just some logistics. As I said, there was going to be an opportunity later to follow along with the R code. And I'll walk through the steps on how to get to it on RStudio Cloud. And I will make this presentation and the code, and also various links available to you from RStudio Cloud. You should be able to continue to access it after the lecture. Can everyone hear me okay? All right. But for the first part, we won't think about any code. We'll just talk very conceptually. So please interrupt, ask questions. I may not be able to answer them all, but I'll try. And if not, I'll direct you to some researchers or some people who might be able to. So I thought it'd be a fun way to start off. I got this email yesterday from A-Star, and it's talking about all of the Chinese New Year treats that people may have had this last week. So you see the top one, that one slice of the bakwa is 301 calories, and they said to burn off one slice of this, it would take 30 minutes of running. And then they give a bunch of more other foods and talk about equivalent physical activity that would burn it off. So I just wanted to start by thinking, okay, what are the sort of assumptions that underlie this? What is the message? What are they trying to do? And what are the different causal questions that we could come up in relation to this? So any thoughts, first of all, what the sort of general underlying message of this one was? I think the title of the email was that it's payback time. Any thoughts? There's no wrong answer. Okay, so there's a net effect of eating these treats. Okay, so that's one thing. And then it's also desirable to negate that, okay? Anything else? All right, so that's sort of my impression as well. First of all, that it's undesirable to gain weight, which may not be true for everyone, right? For certain people, it might actually be beneficial to gain weight. Okay, but in general, maybe on average, people want to, like the weight that they're at, they want to maintain that weight. And so what is the approach if you do eat these other treats that you need to take to negate that? So other assumptions that underlie this, right? If you eat these treats, you also will have eaten the other foods that you would have eaten otherwise. It's not net negative, right? You would eat those foods plus these on top of it. Otherwise, the talking about how many calories of it doesn't really make sense, right? Because you could eat 301 fewer calories elsewhere, and why would you need to do any exercise? Or what else? Any other thoughts on this? Assumptions, questions? Somebody must have some thoughts about this. Why is that? Right. Yeah. Well, it's more, isn't it? It's 35 minutes. Yeah. Oh, so you're saying that underlying this assumption is that different number of minutes of exercise may be needed because the calories that it burns from each activity is different. Right. Well, I think one of the things that it's trying to say is that, okay, they know how many calories generally. They take this and they stick it in the bomb calorimeter and figure out how much it burns. And then they equate it to an equivalent amount that you burn, an average person would burn from a particular activity. So important things to consider there, that there is a distribution of how efficient both you metabolize it and also, and you wouldn't necessarily know this if you don't do this particular research, how much you may burn from a particular activity. People may, 35 minutes of swimming for me is maybe just splashing around in the pool with my kid, whereas for somebody else it's swimming laps, right? So there's some specificity about the particular activity that's important as well. Okay, so no real answers or message from this other than defining a causal question is quite challenging. So how can we be productive about this? How can we translate the questions that we're interested in answering into statistical questions that we can answer with data? That's the biggest question. That's the question we're always trying to answer. What you reviewed yesterday was that one approach that we use for causation and causal questions in the statistical health sciences literature now more and more is talking about things in counterfactual terms. So a cause produces an outcome that's different from what would have been observed in its absence. And of course, we don't observe that. We only observe what actually does happen. So we have to come up with some theoretical frameworks for how we define these other quantities, and we do it in terms of potential outcomes. So the potential outcome for a binary variable x on some outcome y is expressed by the superscripts. So what y would have been if x is equal to 1, if set to 1, or y equals x is set to 0, didn't eat that food. All right. It would be trivial if we had some magic time machine to be able to observe these for all people, giving them or not giving them some particular treatment. In that case, we would just take the mean or the expectation of what the potential outcome would be under treatment, turn back time, look at what it would be if it were 0, and then take the average, take the difference in the means, and that gives you the average causal effect of that particular exposure. Of course, we cannot, at least in this world, do those kinds of experiments. So generally, we have some sort of observational data. And I would even include trials in this as well. We have a certain set of assumptions underlying trials that mimic this particular behavior because we don't ever, at one point in time, observe two outcomes. So observational data can be seen as an incomplete subset of the potential outcomes of the ones that we do observe given a particular exposure level. And furthermore, we talk about confounding in epidemiology at least. We can think about it actually in terms of the bias in the subset of observed potential outcomes. So for example, in a particular drug trial, in a particular observational study of a drug, we might see, for example, that those who are taking the drug actually have a distribution of poorer potential outcomes than those who don't take the drug. And we consider that confounding by indication. But if we were able to account for that and really replicate the set of potential outcomes that we would see under no treatment, then we would hopefully get an unbiased effect of that particular drug. And so there's a certain set of fairly well-defined assumptions, but how they come about is less well-defined, about how we translate the observed statistical quantities into those potential outcome quantities that we are really interested in. So if you have a set of confounders C, a binary exposure as we talked about before, and a continuous outcome Y, one of the things that helps us move from the observed quantity to the potential outcomes quantity is exchangeability, meaning that the value of X is independent from the distribution of potential outcomes Y, what I just talked about basically, conditional on a set of confounders. So if we condition on a set of confounders, X, or the assignment of X, no longer tells us anything about what the potential outcomes would be. That's what we do in a trial, right? We separate a bunch of people, we separate their potential outcomes so that they're evenly balanced between the two, so that once we give them that treatment, the treatment itself doesn't tell us anything about what those potential outcomes would be. We just observe what they would be under that treatment. Positivity is a requirement for the data. In order for us to be able to justify exchangeability or estimate exchangeability, we need to be able to see at every level of a confounder that there is some people with that treatment. If you think about basically estimating things from data, if we don't have any data on one particular group of people, then we can't sort of project that into a model about how people get treatment. So we need to have this data support. So basically for binary exposure, sorry, that should be X, the probability of it has to be greater than 0 at all levels of the confounder in order to be able to estimate potential outcomes. So this one is consistency is the trickiest, and this comes back to understanding the causal processes, the exercise that we started at the beginning. So consistency can be stated in a number of ways, but it's basically saying if we set X to X, X to a certain particular value, then the potential outcome is the one that we actually observe. So this is a bit confusing, but basically what it means is that sort of more casually speaking is if we give somebody a certain assignment, we're guaranteed to know how they would respond to it. So in the example from the beginning, if we just say 30 minutes of swimming, and we don't necessarily define what we mean by 30 minutes of swimming, if we just say we give somebody 30 minutes of swimming, we don't know what the potential outcomes would be. It's not well defined because it could be 30 minutes of lap swimming. That's something different. Maybe 30 minutes of near drowning because the person can't swim. Those will have different outcomes on different sets of potential outcomes for them. So it really comes down to a very well-defined causal question in order to be able to make that assumption of consistency, that if we give somebody a specific level of treatment, that the observed outcomes will follow from what we actually do observe. If we fulfill these, and a number of other ones I'll come back to, we can take the observed data on the left, so the mean of the y, given we've observed some value x and conditional on the confounders, we'll map that directly to the potential outcomes that would have been observed conditional on those confounders. So what does that mean in practice? So I tried to give some examples before. How do you translate that question and obtain an estimable causal contrast? So the basic idea is, can you justify that the potential outcome distribution is conditionally independent from the observed exposure level? So that has to do with exchangeability we just talked about, but also specifying the correct model. You have to have the right confounders in the model. You have to write the causal relationships and conditional relationships in the model. That requires you to know enough about the outcome or disease process to be able to map that out. You need to know the other things that influence that disease process and whether or not their distribution differs by some exposure status. And for those trained in epidemiology or biostatistics, it should come quite naturally to you. This is the sort of things that we think about when we think about confounding. From a data perspective, we have to have enough observational units at each level of the exposure and covariates to be able to properly model the potential outcomes under treatment or no treatment. So that's a positivity assumption. So another way to state the consistency assumption is that does the effect of the exposure vary based on how that level is attained? And there's a lot of talk about this. So you think about things that we sometimes take effects for example, the effect of education, right? Is it the effect of obtaining some sort of certificate or diploma? And do we measure just whether or not somebody has that diploma? Or is it actually all of the learning or the social connections that happen prior to that? Because if I were to just hand somebody a certificate or diploma, that's not going to have really an effect on anything, right? On earnings or jobs. Or it could. Maybe you can use it to con your way into a job. But the specific exposure, how it's attained, has to really map to a set of outcomes. And if we can't define a good mechanism that happens, you probably will not be able to ask a good causal question. So here's an example. So where's the effect of smoking on body weight? Maybe a very sort of general question that you would ask, but it doesn't translate very well to a causal quantity that you want to estimate. So what might be better? Okay, so let's define the exposure a little bit better and the specific population you're interested in a little bit better. Among individuals who ever smoked versus never, it's also quite difficult. These people differ in quite a number of different ways. Among any individuals who smoke 10 versus 11 cigarettes per day, I don't know that this would be a question that anybody would ever ask, because with all the trouble and differences in measures, it's very unlikely that you're going to be able to see a difference in this particular, even if it was very interesting to you, this particular number, you wouldn't be able to estimate that very well. But perhaps you could imagine, for example, a trial amongst people who smoked daily for 10 years and then were able to stop. So we'll come back to this as an example. But each one of these questions, you can imagine, has a different contrast, a different set of relevant confounders, because they apply to different people, different kinds of people. And for example, the middle question of 10 versus 11 cigarettes per day, we might not be able to estimate from available data if the exposure measures we have don't allow us that level of granularity. Okay, so this hopefully is a little bit of a rephrasing or review of the ideas we presented, that were presented yesterday. So how do we extend this? How do make what is a longitudinal causal question, and then how do we go about thinking about it? So longitudinal data fairly easily is just any repeated observations over time. So they could be what the exposure changes over time, the covariates change over time, or the outcome may occur more than once, or some combination of them. And I think the thing that's important is that you actually believe that such variations are important to the question that you're trying to answer. We know that things fluctuate. So for example, you might be interested in the effect of some blood pressure medication, and you're measuring blood pressure over time. But as we know, throughout the day, throughout weeks, they may fluctuate, but it may not be actually important to the causal question you're actually trying to study. Maybe you're just interested in the average over time. And if that's the question, you still only have one exposure and one outcome. There's not necessarily a need to make this a more complex question. But say that you are. And one example where oftentimes we are interested in a longitudinal causal question is if we're interested in mechanisms or mediation. So think about the question sort of rephrased from before, which is, what is the effect of smoking on CVD risk independent of its effect on body weight? Okay, so this is one example where we're interested in a dependency between different exposures or different covariates over time. So we also have to define this question a little bit better. Does independent mean intervening, to have a second intervention to make everybody have the same BMI? A lot of times when we do our statistical approaches, that's actually implicitly what we're trying to do, but is not a realistic intervention that we would do or want to have. Intervening to prevent anyone from gaining or losing weight after treatment. There's actually an interesting study about, I don't remember exactly what the dietary treatment was. I think a low-carb diet. And they were very specific about making sure that on this particular diet, people didn't lose or gain weight as an explanation. Really interesting, very elegant trial, very difficult to do. But that could be one question that we're interested in. In some particular magic world where smoking doesn't affect BMI, or that body weight doesn't have a reverse or a sequential effect on choosing smoking, because we do know that some people choose smoking actually as a weight loss because it reduces appetite. So people do choose it to help lose weight. So there's a feedback relationship too that we need to consider. So again, how we specify that question determines how we try to go about an answer and estimate it from the data. And one thing that I hope that was conveyed yesterday is that in order for us to really get any grasp on what question we're trying to answer and what information we have to answer that question, we really need, I think we really need to diagram it out. So you did discuss causal diagrams, graphical approaches yesterday. So I think that that's actually critical. So here's an example where this helps, and this is how we get from a causal question to a longitudinal question to what exactly is a complex causal question, what we're trying to talk about today. So you might diagram this with your x here as your exposure. It affects some intermediate. So for example, the BMI in the last one we were talking about. Some continual treatment here. So at time 0, here's a treatment at time 1, and some outcome that you're interested in. So with this one, we don't consider it complex. Why? Because in order to estimate the effect of x at this time point, if you'll remember back to the rules that you were given, the deseparation rules you were given yesterday, all you have to do is just look at this association with this. There's no confounding, there's no backdoor pathway to y. Same thing here. If you look at this, and then you condition on z and x, then you have no problems. You can estimate the effect of x at time 1 on y, conditional on z and x, and there's no other things that can bias your results. Okay, so what would be a complex example? So if, in fact, this BMI, for example, if we're talking about BMI, affects your desire to smoke at this point in time, then we have a complex longitudinal question. So what's the difference? The difference is that you have a confounder of this relationship that's actually a mediator of this relationship. So we call that time-varying confounding, because it's a confounder here for this relationship, but it's actually a mediator. It's part of the effect of this previous time point. All right, and we'll talk about why that's a problem and how to deal with it. But that's the difference here between not complex and complex. All right, so this just has regular confounders in it. This has one where a confounder is a product of a previous exposure. Question, yeah? Sure. So let's say that it's, well, I will give more specific examples of this, but while we're on this slide. So for example, take the smoking example from before. You are or aren't smoking. Let's just say that it is a well-defined causal question. Are or are not smoking at this time point. This is BMI at this time point. So it may affect this. It may affect some risk or some biomarker at the end of the day. Smoking at this time point, smoking at this time point. So as we said, for example, if it changes, so say that your goal is actually to lose weight, right? You start smoking, you actually, your BMI goes down, there's reinforcement, so the probability of still smoking at this time point goes up because you're reinforced on that, right? So there is a feedback between exposure at one time point and the other. And so we'll talk about what the challenge is in estimating effect in this. Okay, so here's some more examples. What is the effect of taking antiretroviral therapy, which is for treatment of HIV, on CD4 counts as a measure of immune function? What is that effect, taking into account the effect of changes in HIV viral load on subsequent treatment? So this is where a lot of these methodologies were developed, because people were interested in continual treatment by antiretroviral therapy, knowing that decisions on whether or not people get treated in an observational setting change based on their health status, right? If things get worse, they will be more likely to be continuing on treatment. Another one related to trials is, what is the per protocol effect in a trial of aspirin intake on pregnancy loss? So there's some observational evidence that taking aspirin either helps with conception or helps prevent pregnancy loss. So in a trial of it, there may be varying compliance. So this is any trial. In any trial, there's varying compliance. the drug itself or the treatment itself may cause side effects, or it may cause people to drop out of the study. All of these things will bias actually our effect that we estimate in the trial. So one way to try to fix that is to actually try to estimate a per protocol effect that accounts for these differences or these changes over time. Okay, so this is like the complex one that I showed before, but a bit more complex and a bit more probably in line to what sequential or time-varying treatments would look like. So you have some treatment that may be A, that may be affected by a baseline set of confounders L. Those progress over time, and the treatment decision progresses over time, and they have this feedback between the two. And then you also have a set of sort of unmeasured confounders that affect all of those variables. So in this setting, knowing that what we know about the rules in DAGs and causal diagrams, how would you go about estimating the causal effect of the baseline treatment here? I'll lead you a little. What is the sufficient set of confounders to include that would allow you to estimate a treatment effect of A0? It's not a trick question. Go ahead. Yeah, that's right. So basically you want to take away all backdoor paths from A0. So A0, this is forward, that's okay. So we're okay with these covariates changing over time if we're just interested in this because it's a consequence of treatment at this time. The only thing that's a problem is this right here. And if we condition on this, it also blocks the backdoor pathway from U. So L0 by itself will give you, okay, will give you the effect of A0. Okay, how about A1? L1 and A0. Right, so this blocks this backdoor pathway, this blocks this backdoor pathway, which also includes the path through L0 and U. Right, so this set right here gives you, if this diagram is correct, it gives you the causal effect of A1. Okay, what about the effect of continual treatment across this entire time? Or just a more simpler question, what's the effect of A0 and A1 together? Constant treatment across those two time points. Anyone? It's okay to think out loud. L0 and L1, okay? L0 and L1. So can you, okay, so L0, that makes a lot of sense, right? Baseline confounders, we should always adjust for baseline confounders. Can you give a rationale for why you want to control for L1? Right, so you want to block this backdoor pathway for A1, right? But what you know here is that L1 is partially determined by this. So then you eliminate some of the effect of A0. So the thinking is right. I mean, we do want to condition for, or we do want to account for this somehow, because this biases the effect of A1, but then it's also a product of A0. So in fact, it's not an easy question to answer. So this is sort of what we'll spend the time trying to figure out what the problem is and how to answer that question. Okay, so to answer this question, we think about the identifying characteristics that we had talked about for the causal question in the beginning, where we have potential outcomes, where the superscript for Y gives you the potential outcomes under different levels of treatment. And we add some notation. Some notation is a bar over the variable name indicates the treatment history. So this bar of LT from here just represents what the different values of L took over that time. AT is the same, so the history of treatment through A, bar A. And then you can specify very specifically here, A bar is equal to, or in curly braces, 1, 1, meaning that at A1, it's 1, and at A0, it's 1. Okay? That's just some slight extension to the notation before. So we extend exchangeability to say not only is the potential outcomes for Y independent of the treatment assignment for A1, but it should also be conditional on the covariates and the previous treatment time. So it's just an extension that you add previous treatment as a condition for sequential exchangeability, because as we saw in the previous one, the backdoor paths for A1 include both A0 and L1, as you said. Sorry? Yes, but in this case, it's just it can be with the bar. This just represents the particular value. Because I didn't assign a value, it doesn't matter, but it is the value at time 1. So just this one here. Yes, that's right. That's right. And it's really just to reduce the notation of it. So yeah, L bar and A bar are both vectors of the different values for the particular assignment at those different time points. Up to T, for example, L sub T is through T. Positivity, again, is extended that you have to have a positive probability of observing that exposure at that time point, conditional on both the covariates and the previous treatment. So sequentially, we have to have people at all levels of both the exposure and the confounders in order to be able to estimate the potential outcomes there. So as far as this goes, it's a pretty standard extension from the non-longitudinal one. You just add the treatment histories or the covariate histories prior to the one that you're estimating. Where it differs slightly is that you can think about more than one set of potential quantities that you're interested in. So you may be interested in the effect of A0 alone. Okay, there's a typo. That should be A1. You could be interested in effect of A1 alone, and you can map that to the conditional mean of A1 at that time point based on its previous values. But you could also be, so this follows from what we were saying before. You can estimate the effect of a point exposure. But what's new is that you may be interested in the effect of continual exposure. So what's the potential outcome for A bar 1, meaning the effect of treatment at time 0 and time 1, conditional on the covariate history, and then we need to be able to estimate that. So what we just discussed is that this can be fairly simple. You just condition on A0, L1. This has presented some problems. So consider that this increased treatment at this point in time is indicative or caused by the fact that health or this intervening covariate has declined over time. So that in this treatment group, there happen to be people that are slightly less healthy than they would have been if we had imagined, for example, a trial in that time point. If we had randomized people, the people who are actually receiving this treatment in this time point. So what do we do? Obviously, we condition on L1 in order to deal with that for A1. But the problem is, and I don't know if you talked about collider bias, but even without thinking about collider bias, if you condition on this, it blocks some of the effect of A0. So A0 may or may not have an effect on improving health status or these covariates at this point in time. So it's basically damned if you do, damned if you don't. You trade off reducing bias for the estimating of the effect of A1, and you introduce it in estimating the effect of A0. If you had estimated them both separately, it's not a problem, but you're interested in the joint or continuous exposure across time. And we'll give some more examples about this because this is really critical, but one of the sort of foundational rules in looking at causal effects is that you have to be very careful when you try to adjust or condition for anything that's in the future of your treatment, which is why in randomized trials, generally it's only recommended to do the ITT. Just leave them in the groups they were assigned, estimate the outcomes afterwards. If you try to manipulate any of the exposure groups afterwards, you end up with problems. And these are the sorts of problems that you end up with. Sorry, intention to treat being a particular analytic method where you just compare the difference in outcomes between the groups as they were initially randomized or assigned, regardless of whether or not they took the treatment, whether or not some other events happened. Okay, so the whole purpose of this is, now that we're at this point, how do we actually get to estimate this problem? All right, estimate this question. So a fairly basic example from, this is Miguel Hernan and Jamie Robbins' causal inference textbook, which is actually available for free online. And there's a link to get to it. So if you're interested in much more than just this, I would highly recommend going to that textbook. So imagine we have this very basic but sort of arbitrary example where you have a treatment at time 0 and a treatment at time 1. It's binary treatment. And we know for a fact that there's no actual effect of that treatment. The causal effect of that treatment is 0 on this particular continuous outcome, y. And that's represented by the fact that there's no actual direct arrows between those treatments and y. We also know that there is a sort of prognostic factor in between the two of them, and that being on treatment makes it, so you can think about this as a treatment decision. In their example, I think this is on ART treatment on HIV viral load or something like that. But the idea is that if you're on this treatment at this time, it does reduce the probability that you will be on treatment the next time. Some sort of health indicator improves in this time point, makes it less likely to be on treatment this time. And then the ultimate outcome you're interested in is some sort of summary measure of health, where a higher value means better health. So I think so for example, 44 is less healthy than 84. All right, and then there's some unmeasured health status confounding between L1 and Y. So this is the general setup for it. The other thing to know is that you're more likely to be on this treatment at A1 if L is equal to 1. So the probability is here. So if L is equal to 1, meaning that it meets some threshold to be treated, it's 80%, otherwise it's 40%. You're less likely to be treated at this time point. So we want to estimate the effect of treatment at time 0. So we can look at the mean of this outcome given that A1 is equal to 1. So how do we do that? We take all of the columns here. So the columns here are the number of people observed, what their treatment covariate and treatment at time 1 status is, and their mean outcome, the outcome that we're interested in. So the mean outcome for the A0 equals 1 treatment is just take all of these and all of these outcomes, right, and weigh them by the proportion of the total population they represent. Does that make sense? This is sort of an important point, but sort of a simple one to go to. So to find for a population, right, what the mean outcome is for that population, you just take the means of each of those individuals and you sum them weighted by how many of them they are in that total population. All right? This is it's a principle of standardization that's going to carry through the entire thing. So as long as that's clear. Okay. So we do that for these guys who are treated at A0 equals 1. Take these probabilities. I made it shorter. I reduced the fractions, but you can trust me. It's the right math. And you find that the mean outcome for those who are treated at A0 equals 1 is 60. And we do the same thing for this group right here. A1 is equal to 0. Also is 60. So we get the correct estimate, which is that there is no effect. And given our causal assumptions about identifying the particular effect are true, then we find that the effect of treatment at A0 is equal to 0. All right, we're good. So that part's fine. And we can also show for treatment at A times 1 conditional on A0 and L1. Okay, so how do we do that? Well, we can just look within that strata, within each strata that are consistent for A0 and L1. So what do I mean by that? So say the effect of A1 amongst those who are L1 equals 0, A0 equals 0. All right? That's the effect of A1 amongst that particular group that has both the A0 and L1 values to be the same. And you can see very quickly across each one of those that holds. So conditional on L1 and A0, we have an unbiased effect of A1 as well, right? Which is what we showed with the diagram. For A0, for A0, because there's nothing here, you don't have to condition on anything, you find the unbiased effect. For A1, if you condition on both this and this, then you get an unbiased effect, also 0. All right, so the problem, the total effect here. So say we were to choose the option of not doing anything for L1, the covariates for L1. We could just estimate the group, the mean for the group that's totally treated. So at A0 equals 1, A1 equals 1, and find their means. All right, so this is the here, treated at both time points, here and here. Take their means amongst that total population. Do the same thing for never treated at either, and you get this, which is a biased estimate. Why? Because we didn't account for the confounding by L1 on A1. So the treatment effect of A1, that part is biased. So we sort of knew that already. We knew that if we didn't do anything to account for L1, then we're in trouble because we have that confounding or that bias there. Okay, so what if we try to adjust for A1? What happens? So for adjusting for A1, we can look at both treated versus both untreated in the stratum where L1 equals 0. Does that make sense? We're just looking at conditioning on L1 is equal to 0. We look at both treated 1 versus both untreated 0. And what do we have? Also biased, -8. So why is that? Why do we get a biased estimate when we condition on that? And that boils down to specifically the joint stratification on looking at A0 equals 1 and L1 equals 0 together, and then A0 equals 0 and L1 equals 0 together. So intuitively, you look at this particular group right here, where A0 equals 0 and L1 equals 0. What are those people? Those people who were not treated at time 1 or time 0 and also had no indication of treatment for time 1. Remember that 0 means they're healthier, they don't need to be treated. 1 means they do need to be treated. In this group right here where they didn't get treated, but they still did better, that group is on average healthier than all the ones who may or may not have been treated at A1. Does that make sense? It's a strange selected subgroup of people who did well no matter what. Rather than actually randomizing at time 1, we actually have a biased group right here. So this group, you can see that their health stat, the summary health status is greater, 84 is greater, and so you get that bias here. So you can imagine that a mirrored thing is happening with this group where you stratify on L1 is equal to 1. So this is, again, you're taking the stratum where L1 is equal to 1. In this one, the opposite has happened, which is that you have this stratum right here where they're treated, but then they're still sicker anyway. So this first comparison group where they're treated at both time points, that group is sicker on average than a random draw of people who may have been treated at A1. And then you see the same thing here, right? This value is lower than it actually should be relative to the untreated group. All right, so this particular collider stratification bias where we try to stratify on some measure that comes after treatment is very problematic because it creates these aggregate groups that are not what you would expect under a randomization type of scheme. So how do we deal with this? So rather than stratification, so this is basically a summary of everything that's going to come afterwards. Rather than stratification, we use a different approach to try to account for the confounding at time 1, the L1, and that's by standardization. As we just discussed, we can think about a mean outcome as a sum of all of the conditional outcomes that came, a weighted sum of all the conditional outcomes from the other preceding covariates. So the mean of y is equal to the sum across all the different probabilities of having L, and then all the different probabilities of having A given L. All right, that's what we were showing with the standardization approach before. Right? We just take the weighted mean of each basically type of person. We take the weighted mean of people who are A10, L11, A11, L10, etc. So it's just the law of total probability. That's how we get the mean for a group. So how we translate this to the causal case is that if we take our causal assumptions to be true, we can first replace all of the conditional probabilities of the treatment. We can take them out because we're actually assigning that they are random, conditional on the covariates. We can then map assignment of A to the potential outcome given A. And this is the basic G formula, I think that was introduced yesterday, which is equal to basically the weighted sum of all of the means given a treatment and its covariates on the, basically a function for the probability of the covariate. So for a binary one, it's just the probability of that particular covariate. And then extending it to the time varying factors, as we said, the weighted sum of each one of the different treatment combinations and covariate combinations weighted by the covariates, excuse me, weighted by the covariates instead of just the baseline covariates, then the covariates for the particular effect that we're trying to estimate. So for L1, it's the probability of L1 also conditional on the probability of, conditional of the probability of L1 given A0. Right? So rather than just the baseline covariates, it's also the probability conditional on the previous treatment. So it'll make more sense as we go through some more concrete examples. All right, so applying that particular formula to this question that we have. If we want to estimate the potential outcomes under treatment at both times, it's the sum of the probabilities of treatment at both times and L1 is equal to 0 times the probability that L1 is equal to 0 given that treatment occurs at A0, right? Because we're linking here treatment at A0 with the probability that it's equal to 0, right? We're specifically linking the fact that L1 is a biased sample of all of those that happen, of all the treatment modalities that happen beforehand. There are going to be more people that are L1 is equal to 0 if they were treated. Because that's what we said. We said that treatment at A0 is more likely to be L1 is equal to 0. Plus the treatment across both time points and L1 is equal to 1 times that probability, which we know that to be a lower probability. Right? So it's the weighted sum of the individuals who were observed on treatment at both times by the probabilities that they were having, by the probabilities that they had that confounder level. So it balances the confounders by standardization. And when you do that, very happily, you get the result that we wanted to get, which is that for A1 and 1, it's 60, and A for 0, A0, when we do the same thing with A0, is also 60. So then the total causal effect of both time points is what we expect, which is the sum of their effect at either time point, which is 0 plus 0, which is 0. All right. So it's sometimes easier for people to visualize this rather than looking at the equations. So what we have observed here is, say, a trial of 32,000 people. Half of them were randomized to A0 equals 0, and half of them to A0 equals 1. And then we followed them through. Let's take this bottom branch of the tree here. Of those assigned to 1 at A0, half of them, is that right? Had L1 equals 1, half had L1 equals 0, and then we observe their treatment here, their biased probability of treatment based on what it was at L1, and we have these conditional distributions afterwards. So that's what's observed. And what we want to do through standardization is replicate what would have been observed if we had actually been able to assign them at time 1 to be treated, which is what we computed from that first conditional probability up top. Given that it produces some covariate distribution at L1, and then reassign them. This is the big difference. If we could re-randomize that, balance this population out to receive the treatment at this point in time, and then further assign them to time 1, A1 equals 1 in both of those arms, and then we would get all of those people at the end of the day, their mean outcome, and that would be a weighted mean of if we had actually been able to assign them, randomize them to 1 at this time point, and randomize them to 1 at t equals 0. So the standardization process is basically can be considered if we have sufficient control for confounding to be able to say that we've randomized at both this time point and this time point, a simulation of a sequential randomized trial. And the standardization gives you that estimate there. And this is the basic premise for how this computation process is done. So before I showed you the G formula, which was just the sum of the conditional means given exposure and covariate history times the probability of the covariate and exposure history. By extension, because the settings that we usually work in are probably more complex, they have more time points, we can generalize it to, rather than computing directly what the mean is in each stratum, for example, to put functions to those means. So for example, if our outcome is continuous, we might estimate the conditional mean by linear regression. And then we estimate the probability of treatment at each time point, or the probability of covariates for binary covariates by logistic regression. And when we do this, and this is what we'll do, it's called the plug-in or parametric G formula, because we're actually using parametric equations to estimate this rather than computing what they are for each strata. So an overview of this before we take a break. Most important step, I think, is to draw that causal diagram representing what your causal structure is. If you can't do that, if you don't have that, you really don't have any way of being able to try to figure out what sort of steps you need to take to be able to estimate a proper causal effect. Because all of the conditional dependencies that you have, that you will be modeling, come from this DAG. You need to be able to show sequentially how things are related, how things are interrelated as either confounders, covariates, or mediators. And in the causal diagram, the DAG really helps you do that. And it gives you the rules that you would have to follow in order to estimate effect in those settings. You use parametric models to model the structural relationships, how each things are sequentially dependent in time. And then you run that simulation that I showed on the other page. You take a draw of the baseline values. You use your equations to estimate basically what that mean is at the end of the day. And you repeat that, setting the levels of exposure that you want to. So for example, treatment at both time points, you force treatment at A0 equals 1 and A1 equals 1, and then you model the outcomes using that. Then you do the same thing with 0, 0. And that gives you the estimate from that. That gives you a simulated estimate of that hypothetical experiment if you could randomize both time points. And then because we like to express uncertainty, you can bootstrap this process to get the standard errors or the confidence interval for that estimate. All right, so just in time now to take a short break. And for those who are interested in, I'm going to run through a couple of R examples for this. So if those who are interested in following along, you can take a break or do this while you're taking a break. We have 30 minutes, but I think maybe we'll come back a little bit early, 10:20. But in the meantime, I'll walk you through some steps to set this up. So whoever has a computer and you feel like following along, here's what you have to do. So go to this link. Also, let me know if you have any trouble with Wi-Fi. Are we there? All right, so if you're at that page, you just go ahead and if you don't have an RStudio, this is RStudio Cloud, which is basically just RStudio run on a server. Very convenient if you want to work on a computer that doesn't have RStudio, or if you just want to share your project back and forth. And also, I have to say it's okay if you haven't used R before. The code will be very easy to follow along. You just have to click play. If you're on this page, then you just sign up, create an account, give yourself a name, and once you're all signed up and verified, you will get yourself to this page. So like I said, we'll come back, if it's okay with you, at around 10:20. Otherwise, I'll be here answer questions.